Um, Hi, everyone. Thank you for attending my presentation. So given the time limitations, we won't be able to go too deep into ours. It may take way, way too long. Instead, my goal today is to lay out the design foundations of the Soroban authorization framework and also highlight the features that make Soroban smart contracts safer without any additional effort from the smart contract developers. With that in mind, let's take a step back from Soroban and talk about authorization in smart contracts in general. So from a smart contract perspective, blockchain is just a key value database, basically. And each smart contract just gets their own private table in this database. For example, here you can see token contract storage, very simple model. The key is the user and the value is their balance. For example, it has $1,000 and Bob has just $10. And also, since blockchain is a public thing, all the smart contracts operations can be interacted with by any user. So let's say we want to transfer some money from one account to another. And Alice sends a message to the contract that says, transfer 10 USD from Alice to Bob. That's all right. But then don't forget that anyone can interact with the blockchain. And of course, Bob can say, well, transfer $1,000 from Alice to Bob and drain Alice's account, which Alice obviously did not want. So we need to do some authorization, obviously. Now, we start with the basic thing, which is the operational authorization. Every smart contract operation needs some policy defined by this operation. For example, in case of token, it would be transfers have to only be performed by the user who is the source of the transfer. Basically, the operation authorization policy is who does what. So continuing our example, Alice would say, I'm Alice, transfer 10 USD from Alice to Bob. And obviously, since Alice is the source of the transfer, this would be a valid message for this policy. However, Bob may say, well, I'm Alice as well, and transfer 1,000 USD from Alice to Bob. So obviously, this is not enough, and we need to implement more policies in our contract. And to fix this problem, we need to do some authentication, which is basically establishing the identity of the user, checking if they are who they call themselves they are. In the blockchain settings, the typical way to do authentication is to use cryptographic signatures. And here we see that we add some signature payload to the Alice's message. Now, Bob obviously cannot modify this anymore because modifying the message would invalidate the signature. However, Bob may send this message again and again and again and drain Alice's account. So we are still not there, right? We need more. And to prevent the issue of repeating the same transaction, we need to also implement replay prevention. And an easy way to do that is to implement so-called nonce, which is basically just a unique value added to the message. Here, for example, it's 123. And smart contract would need to take a note of this nonce. And when it is repeated, it would just reject the message. Now, it seems like Bob cannot do anything that is not intended, right? If they resend the same message, they will only be able to send $10 once, which is intentional. So we're almost there, but not quite, because in reality, things are more complicated. For example, in Stellar, we have multiple networks, such as testnet and mainnet, and of course, for the Soroban, we also have futurenet. So for example, if Alice sends this valid message to the test network, Bob might take it and send it to the main network and get money from Alice, which she did not intend to send to Bob. So this is a context authorization policy, which is basically we need to also add some context to the message. In this case, this is the network where this message is being used. So we end up with this pretty complicated message. And don't forget that this is the message that a smart contract has to process. And every smart contract that wants to be reasonable needs to implement all these policies and process these pretty complicated messages. Now, enter the Soroban authorization framework. What it does, it breaks down the policies and deduplicates them where it is actually meaningful. So operation policy remains on the contract developer because, as I mentioned, it really depends on the exact operation being performed. So here is the only thing that needs to be done compared to the naive implementation of the auth we had at the very beginning is to explicitly mark that Alice has to be authorized, and then the framework does all the magic. Otherwise, this message looks pretty much the same as we had on the operation policy slide way back. Authentication policy is defined by the user, which means that the user has a single contract or protocol-defined contract that performs authentication for them. So every contract does not need to keep replicating the signature verification logic again and again. And context and replay prevention are really universal for every contract, and every contract wants them, and they want them in pretty much the same way. So with Soroban auth, we move this to the protocol layer, and we also add some additional execution context for which you should stay tuned. I will talk more in the later slides. So at this point, some people who are familiar with Ethereum, for example, might ask, wait, but we have msg.sender, which is basically a single user that authorizes the entire transaction, and you then can access this user in your contract, and you basically fulfill all these policies, which I said we kind of deduplicate in Soroban. However, the important difference is that Soroban authorization framework supports arbitrary amount of users, not just one. And it also supports only necessary stuff, like not everything is a transaction, but only the parts that are necessary to fulfill the operation. And this comes with a lot of benefits, such as now contract signers and transaction signers can be decoupled. And of course, there can be multiple parties, unlike the case when there is only a single signer for the whole transaction. And these multiple parties may also sign only parts of the payload, and they may do this asynchronously with big time delay, for example, without involving any on-chain state. It also comes with authentication extensibility and advanced execution context, which I will expand on in the following slides. So speaking of authentication extensibility, enter account abstraction, which is something I've basically already told about. The main concept is that authentication is performed by user-owned contract. Stellar accounts get a quote-unquote contract built into protocol, and it implements the standard Stellar authentication procedure that happens for the classic Stellar transactions. So account abstraction, first and foremost, provides extensibility to the protocol so that we are not locked into Stellar accounts, and neither are any Soroban contracts locked into Stellar classic accounts. But there are other benefits from being able to customize the authentication procedure. For example, you can implement some custom multi-sig rules that do not exist in our current protocol. You can also do signatureless authentication, where it would be based on some on-chain state. And this can be used, for example, to implement subscriptions. You may implement some custom recovery tools based on social recovery, for example, that, again, are not currently in the protocol. And you also can implement some safety features, such as spend limits. For example, you can make an account that the user will be able to set some spend limit on certain token, for example, 100 USD per month, and there won't be a way to spend more than that amount, no matter what is happening to this contract. Okay, now to the complex stuff. What if we want to do something more complicated than just transferring token from one account to another? For example, Alice wants to trade with some swap contract. And the idea of the swap contract is that Alice puts some amount of one token and gets some amount of another token back. It doesn't really matter how it is implemented. So what we are trying to do naively within our framework is that Alice sends a message that asks swap contract to swap tokens. But then swap token needs to transfer money from Alice to its own address, to its own balance, right? And this is explicitly denied by the token contracts policy because, as you may recall, it is, well, the source of the transfer has to be the one sending the message. However, here, the swap contract is sending the message, and it cannot pretend to be Alice. It cannot impersonate Alice. So you could also try doing two signatures, right? So Alice could send one message that asks swap contract to swap money, and another message that actually authorizes the transfer operation. And this kind of works in theory, but what might happen in practice is Bob just takes the second part, because they are kind of two separate messages, right? Bob takes the second message, front runs Alice, and then Alice just loses $10 without any effect, because the first part is contingent on second part happening. So what we come up instead with Soroban authorization framework is call tree context. And this basically allows us to have just a single signature that spans across, that covers the whole tree of various calls. So in our pseudo language of messages, you can see that there is one authorization from Alice, right? Then there is a message for the swap contract, right? Swap 10 USD for 100 XLM. And then there is another instruction, which is kind of standardized in the protocol, that says call token contract from the swap contract and perform the transfer. And this is all single message that is authorized once. So it cannot be broken down because the signature is over the whole thing. And if Bob tries to modify the signature, will get invalidated. And this is generalized to multiple trees, multiple actors, and multiple calls. So here is pre-involved example where Alice and Bob automatically swap two pairs of tokens with one another, right? And you can see that Alice sends a message where she asks to transfer A and B for C and D, and also bundles the respective transfer calls. And then Bob does the same but mirrored, right? Bob swaps C and D for A and B, and authorizes transfers of C and D to the swap contract. And then swap contract can perform the swap atomically. So this all might seem pretty complicated, and it kind of is. But we have a lot of ways to mitigate this. First, it is pretty easy to observe and verify the required authorization in tests, and experimentation is encouraged. We support recording mode, we support the enforcing mode, so you can both explore stuff and you can assert on the exact authorizations that need to happen in the contracts. Of course, when you come to the production stage, transaction simulation can help to record the necessary authorization payloads as well. And this is also useful for the experimentation, obviously. You basically just send your transaction to our simulation service, and you get back the payloads that every actor in the transaction would need to sign. Well, in reality, these trees, not actually that complicated. And probably most of the contracts would want just like 2-3 calls. Typically, it's like send token to the contract and do some stuff in exchange, right? And last but not least, if you look at this from the wallet perspective, where the user needs to sign some pretty complex payload, you can actually focus on the top level and token operations. So basically, the user would see, hey, you're trying to trade with some DEX, and it will do something, but the main point is that it will take this amount of USD from your account. So it can be made very transparent to the users without going into some deep implementation details. Okay, so now to the conclusions and reasons why is all stuff making the contract safer. Well, first, we have a lot of common stuff moved into protocol, which means that it needs to be audited and tested just once for everyone, and it is being tested and audited. So there is a whole layer of code that you don't need to write, and obviously, if you don't write the code, you cannot have a mistake in it. Account abstraction. It really helps to encapsulate users' trust in a single contract. So instead of relying on every contract correctly implementing the authentication procedure for your specific account, you do this just once, and you need to trust only this single account that has implemented it. And then you are not afraid of bugs in some particular implementation of some particular verification algorithm. From the wallet standpoint, as I've mentioned, since all this call tree information is structured and standardized, wallets can implement the logic just once that would trace all the calls that are being performed when contract is being executed and surface it to the user. So it is pretty much impossible, as long as wallet is correctly implemented, it is impossible to take money from the user without user acknowledges that, yes, I'm actually going to send like $1,000 to this unknown address. Atomicity. There is no need to come up with some complex procedures like, for example, token allowances in ETH that kind of are hacks to replace atomicity rate. Instead, you can do pretty complex things atomically with a single signature, so there is no need to implement anything else. And again, if you don't implement something, you won't have a bug in this. And last but not least, the contracts that use Soroban authorization framework are compatible with each other and can be nested and layered together, and they don't need to adapt to each other's bespoke requirements, and they don't need to implement different standards. There is just a single standard. If you implement it once, you'll get it for everything. Okay, so what to read next? There are obviously Soroban docs. There are docs describing what I told here in more detail. There are examples, simpler examples, more complex examples. And this is all on the contract side. For more complete integration story, there is a DApp example, link here, so you can take a picture. Yeah, there is a DApp in React that does atomic swap, which is a pretty complex operation involving two parties swapping atomically, right? And if you want to go really in depth, you can read CAP 4607 that describes the exact specification of how exactly all the magic happens in the OS system. Okay, thank you. And one more thing, if you have more questions, I have a brain date tomorrow, so feel free to just schedule it, and I will answer, or just catch me. Okay, thank you.